Hello students, welcome back to another exciting step in our journey through calculus. We've already seen how differentiation helps us calculate slopes and rates of change. But here's a natural curiosity. What if someone hands you the derivative of a function and asks you to recover the original function? That's exactly what integration does. It is the reverse process of differentiation. For example, if d by dx of f of x equals f of x, then f of x is called an antiderivative or primitive of f of x. We write this as integral of f of x dx equals f of x plus c. So, whenever you think of integration, remember, it is the art of retracing your steps from a derivative back to the original function. Let's take our first example. We know that d by dx of sine x equals cosine x. This means that sine x is an antiderivative of cosine x. So, when we integrate, we write integral of cosine x dx equals sine x plus c. Here, c is the constant of integration. It shows that there are infinitely many functions, all differing by a constant, that share the same derivative. That's why integration always comes with a plus c. Next, let's check a polynomial example. We know that d by dx of x cubed by 3 equals x squared. So, x cubed by 3 is an antiderivative of x squared. In general, we follow the power rule of integration. Integral of x to the power n dx equals x to the power n plus 1 divided by n plus 1 plus c. Remember, this rule is valid for n not equal to minus 1. So if you see an x squared, its integral is x cubed by 3 plus c. Simple and powerful. Now let's move to exponential functions, everyone's favorite. We know that d by dx of e to the power x equals e to the power x itself. So e to the power x is very special. It is its own derivative and also its own antiderivative. That means integral of e to the power x dx equals e to the power x plus c. This property makes exponential functions extremely important in both differentiation and integration. Now here's something subtle but very important. If d by dx of f of x equals f of x, then d by dx of f of x plus c also equals f of x. That's because the derivative of a constant is 0. For example, derivative of sine x plus c is still cosine x. Similarly, derivative of x cubed by 3 plus c is still x squared. This means antiderivatives are never unique. They always come as a family of functions differing only by a constant. Graphically, they look like parallel curves shifted vertically. Let's verify one example step by step. We want to check if integral of cosine x dx equals sine x plus c. Step 1. Assume f of x equals sine x plus c. Step 2. Differentiate it. Derivative of sine x plus c is cosine x. Step 3. Since f dash of x equals cosine x, the original function is confirmed as an antiderivative. So, our verification is successful. Notice that the constant c disappears when differentiating. That's why integration always includes it. Why is this idea useful in the real world? Well, integration is everywhere. In physics, if velocity is given, integrating it gives displacement. If acceleration is given, integrating it gives velocity. In economics, integrating marginal cost or marginal revenue functions gives total cost and total revenue. In probability, we integrate density functions to get distribution functions. So anti-differentiation is not just theory, it turns local rate information into complete quantities. Let's quickly recap what we've learned. Integration is the reverse of differentiation, also called anti-differentiation. We saw that integral of cosine x dx equals sine x plus c, integral of x squared dx equals x cubed by 3 plus c, and integral of e to the power x dx equals e to the power x plus c. Antiderivatives are never unique, they differ by a constant c. And this process of recovering the original function has deep applications in physics, economics, statistics, and beyond. So, that's the foundation of integration as an inverse process of differentiation. In the next video, we'll explore the rules and techniques of integration that make this process practical and exam ready. See you there.